welcome again to Numbers Online School. Today we'll be going through counting principles, and then after that we'll be doing some problems associated to what we have just learned. So basically there are two counting principles. The first is addition principle and the second is the multiplication principle. The addition principle states that if an event A can occur in A ways and an event B can occur in B ways, then the event of either A or B can occur in A plus B number of ways. So we have two possible events, A and B, and A can occur in A ways and B can occur in B ways. As long as either A or B can occur, then we can calculate the number of ways for which either A or B can occur, and it will be the sum of the individual number of ways for which A or B can occur. So it is A plus B. So basically this is the addition principle as used in combinatorics or even in probability theory. Whenever you have either one event to occur or the other, then the total number of ways for one to occur or the other is the sum of the individual number of ways. And the second is the multiplication principle. If you have an event A that can occur in A ways and an event B that can occur in small b number of ways, then the event of A and B and that the event of A and B are the events A and B are independent, then the number of ways in which both A and B can occur is A times B. So again, in this case, you have two possible events, A or B, and A can occur in small letter A number of ways, and the event B can occur in this much number of ways. And the condition that A and B are independent, this implies that the event number of ways in which both A and B can occur simultaneously is A times B. So in this case, we are multiplying the individual number of ways because A and B are independent and we want them both to occur, then here we'll be multiplying. But if it is either A or B, then it will be A plus B number of ways. And in this case, it is important that the events are independent. This is very important. Independent, so that we can multiply out the individual number of ways. So as I said earlier, these principles are very useful in combinatorics and in probability theory. And using these principles, we'll be going through some problems so that we can see how they're actually used in problem solving. So the first problem says that find the number of three-letter words that can be formed using the letters A, B, C, or D. So a three-letter word using A, B, C, and D. So for example, I can say maybe A, B, D. So this is a word. It does not matter whether it makes sense or not, as long as it is a word which consists of three letters A, B, and D, then it fits the category for this problem. So it has to be of length 3 letters, and the letters themselves have to be either equal to A, B, C, or D. So here we have 4 number of ways of filling the 3 spots. So the first letter will be here, the second letter will be here, and the third letter will be here to form the words that we want. So in this case, the first letter is A. So the first letter, the second letter is B, and the third letter is D. So each and every word will be categorized into 3 parts: the first letter, the second letter, and the third letter. And remember, the 3 letters do not have to be different. So for example, I can say maybe A then B, or maybe C, C, C. As long as it has 3 letters, and the letters are composed from the 4 letters A, B, the 4 alphabetical capital letters. So we want to count the total number of words that can be formed using this process. So if we restrict our attention to a particular spot, a particular position of a given letter in that word, so for example, the first place, this first place can be occupied by any of the four given letters that we have on the problem. So in this first place, we can put an A, we can put an B, we can put a C, or we can put a D. Okay, so this first place can be occupied by any of the four initial letters that we have. Same goes for the second position. For the second position, you can also put either A, B, C, and D. And the letter on the second position does not depend on what the first letter was. So for example, if here I had put C, then the next letter can be any of these four. So it can be A, B, C, or D. So the first letter does not affect what the second letter will be. So in this case, we also have four number of ways of filling this spot. And for the third letter, we have again four number of ways of filling this spot. So in order to use the counting principles in this case, actually we're using the multiplication principle. We're using the events. So maybe event A, you can name it as the first letter. Now the first letter can be either of the four original letters, A, B, C, or D. So the first event can occur in four different number of ways. That is the first event. The second event is the letter on the middle position, the second letter. The second letter. And again, this can occur in four different ways. We can substitute any of the four letters into this middle letter of the three-letter word. And for the third event, this stands for the third position, third letter, which is the final letter in our case. Again, it has four number of ways to fill it in. So again, we have A, B, C, or D. And most importantly, the events are independent. So for example, in event A, we have chosen C to occupy the first position. Then the second event is not affected by what we have decided for the first event. So the second event can be again any of the four initial letters that we have been given. So by the counting principle multiplication, we can actually multiply this times this times this. In which case we get 64. And as you may notice, here I have put only two events, event A and event B. But actually this principle still works as long as you have a finite number of events. Maybe if you have three events with A, B, and C number of ways, then the total number of events occurring for all of them is actually A times B times C. Even if you have four of them or five, you just multiply them out as long as they are independent and they all have to occur. So you have, in this case, 4 times 4 times 4, which is 64 total number of ways. In this case, you can say that there are 64 number of three-letter words. Consisting of the letters A, B, C, D. So this is our final answer that we have only 64, no less, no more. Yeah. So we move to the second problem. So for the second problem, it says that we have to find the number of subsets of this set here, set A, which contains 10 letters. The first 10 alphabetical letters: A, B, C, D, E, F, G, H, and I, H, I, and J. So what do I mean by a subset? A subset is a set that contains some of a subset of a given set is a set that contains some of the elements of the original set. So for example, maybe my set, instead of being that, maybe it is 1 and 2. So 1, 2, and 3. So a subset can contain some of the letters of the original set. So a subset of B can be 1 and 2 like this, or it can be 1 and 3, or it can be 3 itself, or it can be an empty set. As long as it is a part of the original set, the larger set, then it is called a subset of the original set. So in this case, the total number of subsets of B, we can try to list them down. We have the empty set, which does not contain any element. The second set, the second subset, which contains 1. The second set, which consists of 2. The third, which consists of 3 itself. And then you can go into 1, 2, 1 and 2, and then 1 and 3, and then 2 and 3, and then finally the entire set. The entire set is also a subset of the original set, as long as whatever is in the subset is also contained in the original set. So these are all the possible numbers, the possible subsets of the original set B, which contains 3 elements. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 number of subsets in this case. So using this example, we want to find the number of subsets of this set, which now contains 10 elements instead of just 3. So we have to find a clever way of counting the number of subsets of a given set. So we start with this simple example. We try to elaborate further. How can we count this number of subsets in another way? So again, let's take a look at the ways in which we form a subset. So in order to form a subset, you have to take some of the elements of the original set. So for example, this subset which contains 1 and 2, that means it has taken 1 and 2 and 3 has been left out. Okay, so I can symbolize it by maybe a yes, and a no. Okay, so I take 1, that means I say yes for 1. I take 2, that means I say yes for 2, and then for 3 I say no because I don't take it. So I can categorize this subset into this format. Okay, so either for each element there are only 2 number of ways of dealing with it. You either include it in your subset or you don't include it in your subset. So let's take another look at another subset. If you look at this subset, which consists of the element 2, that means what we have done from the original set, we left out 1, so we can write it as a null for for the first position of 1, and then we took 2, we can write it, simplify it as a yes, and then for the third part, we did not take 3, so we can write it as a no. Okay, so y is for yes and n is for no. Okay, again, you can take a look at another example. So for example, the empty set does not contain any of the original elements, so we have no's on all of the original elements. Remember, the first position signifies the element 1, the second position signifies the element 2, and the third position signifies the element 3. So the empty set, because it contains neither of the elements, it's a no for all of the original set. So as you can see, maybe let me do a last example. For the set that contains all the elements, as you may guess it, that means it's a yes for all the positions. So we took 1, you can symbolize it as a yes, then yes for 2, then yes for 3. So again, what can we say about this other way of defining these subsets? This means that each of the subsets can be represented into a 3-letter word, okay? A 3-letter word. So we have the first position, the second position, and the third position. The first position is for the element 1 in the original set, okay? And the second position is for the element 2 in B. And the third position is for the element 3 in the original set B. Okay, so what we are actually doing here, we are making 3-letter words in order to form this subset. So for example, you can name any 3-letter word which contains either n or y in each of these positions. So for example, maybe I can name yes, comma, I can say maybe y, n, y. Okay, so this is a 3-letter word which consists of y or n. So from this 3-letter word, I can find a subset to represent it. So yes, remember, that means it contains 1. A no in the second position means it does not contain 2, so we skip 2. And then a yes for the third position, that means it contains 3. So this 3-letter word actually represents this subset here, 1, 3. Okay, and for each of the subset, we can form a 3-letter word, and for any 3-letter word with yes or no, with y or n at its position, we can find a unique subset. So in this case, we have found an easier way of counting these subsets in terms of 3-letter words that contains y or n. So at this point, we can find the number of 3-letter words using y or n, just like we did for the first example, which is easier to do because, as we have already saw, we have 3 positions and 3 letters, yes or no. So the first position can be filled in 2 different ways, can be A or N, the events. And the second position is not affected by the third position and can also be filled in 2 different ways, either a yes or a no. The same goes for the third position. And again, these events are independent. If here there is a y, then here can be a yes or a no. It does not matter. They do not affect each other. So in this case, we can again invoke the multiplication principle and multiply them throughout. Okay, so here we have 2 times 2 times 2, and we get an 8. The exact same number of subsets that we counted earlier in this simple example. So when it comes to a larger set like set A, which contains B number of elements, if we try to list them all, it will take us a while. But again, you can use the same strategy here. Of counting the subsets of A as a number of ways to count So we have 10 positions, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? And each time, each subset can be categorized as a yes or a no in each of the elements. So for example, again, a subset maybe like B, comma E, comma H, comma J can be represented as, because you do not take A, we say this is for A, this is for B, this is for C, D, E, F, G, H, I, and J. So because if this subset does not contain A, you can write a no for A. Because it contains B, you can write a yes for B. Then C is a no, D is a no, E is a yes, F, so F is a no, G is for no, as a no. Then because Y is contained here, you can write a yes, then no, then yes. So again, in this case, we can categorize the subset of this set as 10 letter words, for which at each position, each of the letters is either a no or a yes. So again, we can use the multiplication principle. Because they are independent. We can find out that the total number of subsets of that set, it is 2 times 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 2. So there are 10 2's in a row. We are multiplying them out, and so you get 2 power 10, which is 1024 number of subsets. So it's an easier way to count the number of subsets. Instead of listing them out and counting them, we can find another set which is easier to count. In this case, we have found it is easy to count the number of 10 letter words, which either at each spot contain Y or N, instead of listing the whole number of subsets and then counting them. So that's it for the second problem. And the technique that we have used here, it is known as bijection, but we'll see that in the next videos. Okay, for the third problem, we are told to find the number of non-negative integer solutions to x, 2x plus 3y is less than or equal to 7. So what does this mean? This means that we have to find the pairs x, y, for which both x and y are non-negative and can satisfy this equation. So for example, maybe you can set x equals to 1 and y equals to 1. So you can set when x is 1 and y is 1, we get 2x plus 3y equals to 2 plus 3, which is 5, and 5 is less than or equal to 7. So 1, 1 satisfies that equation, that inequality. So we can include it in our set. For the same reasons, 0, 0 also satisfies this condition, so it is also included in our set. So we want to count all the pairs for which x and y are negative. So x and y, they have to be greater than or equal to 0, and they have to be integers. So in order to do that, we can categorize them, okay? When x equals to 0, because x has to be equal to 0, we have to start at 0. When x equals to 1, when x equals to 2, when x equals to 3, and when x is at least 4. So these are the events: event 1, event 2, event 3, event 4, event 5. Okay? And in each of the events, we try to evaluate the number of pairs x, y which satisfy that equation. So in this case, for x equals to 0, we have the equation that when x is 0, we have that 3y has to be less than or equal to 7. So at this point, it is not hard to see that the possible values of y can be 0, or it can be 1, because 3 is less than 7, or it can be 2, because 6 is less than 7. But it cannot be 3, because 3 times 3 is 9, which is greater than 7. And it cannot be 4, because 3 times 4 is 12, which is greater than 7. So in short, all the values of y for which y is greater than or equal to 3, in this case, they will not satisfy that inequality. So we have to stop at this point. So we move at the second event for which x is 1. So we look at the possible values of y in this case. When y is 1, the equation becomes 2 plus 3y is less than or equal to 7. So you can simplify it a bit, subtract 2 both sides, you get 3y is less than or equal to 5. Again, you can start, y can be 0 because 0 is less than 5, less than or equal to 5. Y can be 1. Remember, x always has to be 1 in this case. So in this case, 1, 1 satisfies this equation, and y cannot be equal to 2, right? Because 3 times 2 is greater than 6, and 3 times 3 is greater than 5, and so on. So for all the values of y which are greater than 1, they cannot satisfy this equation. So we have to stop at this point. And for the other part, when x is 2, the equation becomes 4 plus 3y is less than or equal to 7. This implies that 3y is less than or equal to 3. You can divide by 3 both sides, and so you can get y is less than or equal to 1. And at this point, it's not hard to see that the only possible values are when y equals to 0 or when y equals to 1. So in this event, there are two possible number of ways. Okay, the third event, x equals to 3. When x is 3, the equation becomes 6x plus 3y, sorry, it becomes 6 plus 3y is less than or equal to 7, which becomes 3y is less than or equal to 1. So obviously this is only possible when y is 0, because if y is a positive integer, other multiples of 3 are always greater than 1. So in this case, we just have this pair which can satisfy the equation. Now for x greater than or equal to 4, if x is at least 4 here, you can see that 2 times x will be at least 2 times 4, which is 8, and 8 is greater than 7. So at this point, x cannot be 4, right? Cannot be 4 or 5 or 6, because as long as x is 6 and y is non-negative, then this term here will be obviously greater than 7. So for x greater than 4, we have no solutions at all. So again, what we're using here is the addition principle. This is the first event, second, third, fourth, fifth, okay? So since the first event can occur in 3 ways, okay, we have 3 ways for the first event. The second event can occur in 2 ways. The third can occur in 2 ways. The fourth can occur in 1 way. And the fifth, in which x is greater than or equal to 0, can occur in 0 number of ways. Remember, we are using addition principle here because we are using either or. X can be 0 or 1. It cannot be both 0 and 1 at the same time. That is why we're using the addition principle. So in this case, you have 3 plus 2 plus 2 plus 1, 8 number of ways, which is the final answer. So the number of pairs is 8 in this case. Okay, now we are going to the final problem. We are told to find the number of squares with all their vertices belonging to the 4 times 4 array of points below. So let me write down the so we're having this 5 times 5 grid. So there are 5 times 5, a total of 25 points, which are on like a lattice point. They are forming these lines vertically and horizontally, and we have to find the number of squares that whose vertices are contained in this point. So for example, one of the squares is this one here. So this is one of the squares, okay? Because the vertices are this point, this point, this point, and this point, which are all contained in here. So another example is this one. This is also a square because it has 2 units and 2 units, and the vertices, this point, this point, this point, and this point, are contained in this configuration. Another example maybe is the entire thing. A square whose vertices are this point, this point, this point, and this point. And the more interesting squares are those which are maybe lying on the diagonal. For example, this square. Sorry. Yeah, sorry, this square. Yeah, so not all the squares have their sides parallel to the size of the largest rectangle, or the largest square, but there are some squares which are also tilted. So we can use the addition principle here to find the total number of possible squares whose vertices are contained in that configuration. So for starters, we can look at the simplest possible squares, the 1 times 1 squares, okay, whose sides are parallel to the largest square. So we can have here one square, you can have here the other one, the second one, the third one, and so on. So for this row, we can have 1, 2, 3, 4, and so for the other 4 rows. So in total, we have 16. 4 times 4. 4 times 4 unit squares. 4 times 4, 1 by 1 squares. Okay, whose sides are parallel to the largest square. The same goes for, a similar case goes for 2 by 2 rectangles. So you can have one right there, the other one can start right here, and then you can go like this. The other one can start right here, and then you can go like this. So in this, which are contained in these 2 parallel lines, we can have the one starting at here, which is 1, 2, 3, and at this point we only have 3 possible number of squares for which there are 2 by 2 squares and they lie on these 2 lines. So the same case goes for the squares that lie on 2 by 2 squares which lie on these 2 parallel lines, and the same case goes for the one which lie on these 2 parallel lines. So in total, I have 3 times 3 unit squares, 3 by 3, 2 by 2 unit squares, for which their sides are parallel. They are not tilted squares, their sides are vertical or horizontal. So at this point, you can try to see the pattern here. For 3 by 3 squares, you can start over here. Okay, if I do a better example, a 3 by 3 can start over here like this, and then you can shift it to the right, and then we get another one. And that's all we can do for those which are lying on these 2 parallel lines. And then we can try to find those which lie on these 2 other parallel lines, for which again we'll get only 2 3 by 3 squares. So in this case, we have 2 times 2, 3 by 3 squares. Whose sides are either vertical or horizontally. And finally, a 4 by 4 squares, it means it's the largest one because it contains its width has to be 4. Its height has to be 4 and its width has to be 4. So it will be the square that contains the corner points. So there will only be one 4x4 square whose sides are either vertical or horizontal. So again, as I said previously, there are these squares which are lying on which are tilted a little bit from the horizontal or the vertical. So how do we count those? If we look at those squares, we can always find another. For example, if you look at this one, at this square, we can inscribe it in this 2x2 square. Okay, both sides are either vertical or horizontal. So whenever you have a tilted square, so for example, if I have this tilted square that goes like this, then it is perfectly contained in this largest square. Okay, or maybe if I have this one here, then it is contained in this 2x2 square. Okay, so whenever you have a tilted square, then it has to be contained in a square that we have already listed in this initial list. So that being said, we can count the number of tilted squares from these four categories. For the first case, maybe if we start with a simple example, a 1x1 square. A 1x1 square, unit square right here. A 1x1 square cannot contain a tilted square because there are no points along the edges, because there is only one unit. Okay, so in this case, there are no tilted squares. For the second case, 2x2 squares, 2x2 squares look they are like this. So we have a point here, we have a point at the middle, we have a point here, we have a point at the middle, a point here, a point here, a point in the middle, and a point here. So the only tilted square that it contains has to pass through these midpoints like this. Like that. Okay. So every 2x2 squares contains exactly one tilted square. The squares whose edges are not vertical or horizontal. And when we proceed to 3x3 squares, the 3x3 squares, something like this. And at the trisections, we have points. We have a point here, we have a point here, a point here, a point here, 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 and here, like that. So we can again try to find the total number of tilted squares that it contains. You can start right here, and you can go like this, and you can go like this, and you can go like this, and you can go like this. That is one of the tilted squares, and the other tilted square go like this, and then like this, and then like this, and like this. And after that, there are no other tilted squares, and you can take your time to convince yourself that there are no other tilted squares, because if you start at this point, you cannot go at this point here. Why? Because there are no other squares, there are no other vertices for which which lie on the boundary of the larger diagram or the larger square, and for which the distance is exactly equal to this one. So actually there are only two tilted squares in each of the 3 times 3 squares. So two tilted squares. Okay, so that is for this is for the 3x3 squares. And finally, for the 4x4 squares, it has to look something like this. So we have points at the middle, at the edges, like that, and then we have at the quarter points. Yeah. So this is what a 4 by 4 square will look like, which is exactly the largest square which can be contained in that configuration of points. So again, in this case, so when you start at this point here and connect it like this, you cannot continue because the only other point for which the distance is the same is this other point here, and this angle is not actually equal to 90 degrees, so you cannot be able to form a square beginning with this edge over here. So you have to, you can try to convince yourself that when you start at the point like this one here, the only edge which is possible, you have to go all the way up to the other point on the other edge. And so we have to follow the same principle. We have to go until to this point, and then at this point you can continue like this and then connect it like that. So that is the first tilted square. The second one is the one going through the midpoints. And the last tilted square is the counterpart. And those are all the squares which are perfectly contained in the larger square. So there are 3 tilted squares which are contained in 4 times 4 squares. In 4 times 4 squares. So after that, we can try to use the addition principle, because these are independent events. We want to count the squares in this category: number of 4 times 4 squares, number of 2 times 3 squares, 2 times 2 squares, and 1 by 1 squares. So as we have seen already, for the case of 1 times 1 squares, there are 16 of them. 4 times 4, 16. And these squares do not contain tilted squares within the interior. And for 2 by 2 squares, we have seen that there are 9 of them. 9 of them, and each of them contain 1 tilted square. So we can try to include this tilted square in this category by multiplying out here by 2. That means we count the 2 by 2 squares which are for which the edges are horizontal and vertical, and the ones which are tilted but contained in that 2 by 2 square. So we're counting this one and the other one. So there, for each of the 9 2 by 2 squares, there is this exactly 1 tilted square which it is contained. So there are a total of 18 in this category. And for the third category, we have 3 by 3 squares, which you have seen there are 4 of them. And for each of the 4, they contain 2 tilted squares. So if we include tilted squares and the one we are considering, the one which is we saw they are like this. Yeah. We saw like there are 2 of them. So we have 1, 2, and 3. We also include the original 3 by 3 square. So in this case, we have 2 tilted square plus that extra one. We get 3 number of, for each of the 3 by 3, we can find the other 2 which are tilted. And so in this case, we get 12 number of squares. And for the last one, of 4 by 4 squares, we have seen that there is only 1 such square, and that square contains 3 tilted squares. So to also include the original square, we multiply out by 4, in which case we get 4. So again, in this case, we have to use the addition principle and add them out. 16 here plus 18, which I think is 34, plus 12, which I think is 46, plus 4, which is 50. So there are a total of 50 squares for which their vertices are contained in this configuration of points. So I think that is it for today. Thank you for watching, and I'll see you in the next video.